I will break these questions up onto different pages, but in case you just want to try all of them, there they are. So we see here that the table below shows the relationship between melting points of 3 molecules. Okay, so we've got CH4, CF4, and CCl4, and we've got their different melting points. First question says, define melting points. Now, guys, I wish we could just say that it's the temperature when a solid turns into a liquid, or boiling point is the temperature when a liquid turns into a gas. But we're not allowed to say that. Let me give you some theory here. Well, not theory, but like I'll help you with melting point. So we can say it is the temperature when the space and space phase are in equilibrium. For melting point, it's when you're going from solid to liquid. So you could say liquid and solid, or solid and liquid. So it's just when those two phases are in equilibrium. Explain the trend in melting points of the molecules in the above table by referring to the intermolecular forces and energy involved. Okay, so remember, intermolecular, those are the forces that go between the molecules. Those are things like London, dipole, hydrogen. Okay? If they said intramolecular, if they said intramolecular, or if they said interatomic, that's when we're talking about ionic, covalent, metallic. Okay, so explain the trend in melting points by referring to the intermolecular forces. Okay, for 4 marks. Okay, so let's start with CH4. So what we'll do is we'll go draw CH4, and we'll draw 2 of them. Why? Well, because we're looking at intermolecular, so you need to have at least 2, because you need to see what's happening between the molecules. We're not looking at what's happening on the inside. Those are covalent, ionic, metallic. We're not looking at that type of stuff. We're looking at what's going on between them. So the way we do this is we need to know, is the molecule polar or non-polar? Because then it's easy. So if you look at this, so if we look at the electronegativity of carbon, it's 2.5. And if we look at hydrogen, it's 2.1. So the electrons are definitely going to be more attracted to carbon. Remember, the higher the electronegativity, the more electrons are... so if an atom is more electronegative, it means it attracts electrons more. Okay? So these electrons are going to be more towards that side, there, and there. Okay, so we can definitely say that this bond over here is a polar bond. Polar means that there's a more positive part and a more negative part. However, this entire molecule is going to be non-polar. Why? Well, if you just look at all of those arrows, I mean, you've got an arrow going there, an arrow going there, an arrow going there, an arrow going there. They're going to cancel each other out. So this entire molecule, if you look at it as one object, is actually non-polar. It does not have a net dipole moment. So here we've got a non-polar, here we've also got a non-polar. So when you have 2 non-polars, then the intermolecular force between them is called London. Okay? Now, okay, so obviously I'm going to show you how to answer the question, but I'm just giving you the theory or the explanation right now. So London forces are between this one, okay? So we can say London. Now, what I just realized is that all of these are going to be non-polar. Check it out. If you have CCl4, that's also going to cause all of them to cancel out, right? Oh no, these electrons would actually go this way, but they would still cancel. Okay, you can go check it out for yourself. And then if you had CF4, the electrons are going to go outwards, but it's all going to cancel out. So all of these are non-polar molecules. So what is going on here? Well, this is actually a good question. Let's go explain. So, can we agree that all of these are non-polar molecules? Yes. So, there are London forces between this one's molecules, London forces between this one's molecules, and London forces between this one's molecules. So imagine life was so simple that all London molecules have a boiling point of -50 and all hydrogen bonding molecules have a boiling point of like 70, but it doesn't work like that. even within the London forces, there are going to be different strengths. So what affects that? Well, scientists have observed, or they have been able to study this, and they have come up with the following, or they found the following. Heavier or larger molecules have stronger London forces. Okay, but now let me try to remind you exactly what London forces are and what causes them, okay? So we said that London forces take place between non-polar molecules. So let's draw the most basic non-polar molecule we can. We just make up a molecule called AA, and it's got a bond. Now, it's not more positive or more negative. Actually, let's just say it's got those electrons there. And then let's put another one. Now, electrons are not perfectly standing still. They are constantly moving, okay? Electrons are moving. So, what if for a few split seconds these electrons over here are a little bit to the left-hand side? Just a little bit. That would mean for that few split seconds that this one is becoming more negative, leaving this one to be more positive. And what if in this molecule over here, the same thing is happening, where these electrons go a little bit to that side? They're moving at all times, okay? So for a few split seconds, maybe this side is then the more negative and this is the more positive. Suddenly, these two molecules are going to attract, because the positive over here would attract the negative and the negative would attract the positive. Then, in the next split second, maybe the electrons move a little bit to this side. What that would then do is it would cause this side over here to become more negative and this to become more positive, and maybe these electrons switch the other way, or maybe they go further this way. So this becomes even more negative and even more positive. Then there's going to be an attraction over there. That is what London forces are. They are temporary. Okay? They are not permanent, like what we have with dipole-dipole. They are temporary because these electrons are constantly moving. Okay. So that's the basics of what London forces are. But now let's say you've got large molecules or heavier molecules. Now, if you look on your periodic table, then what we can see is that the heavier molecules are the ones, if you look at the mass, 23, 24, 27, 28. These are heavier molecules as we start going down on the periodic table. With those, we are also having more electrons, because here you've got 12 electrons, here you've got 13 electrons, 16 electrons, 34 electrons, 35 electrons. You see the amount of electrons are becoming more. And so let's conclude that heavier molecules means more electrons. Okay. Now, you know what I showed you now with the London forces, and we said that it's because it's these electrons that are temporarily moving a little bit to that side and a little bit to that side. Now, when you have heavier molecules, you have more electrons. When you have more electrons, you increase the chance that this type of thing can happen. Because it's not only the electrons in the middle that are doing this. So let's say you have, for example, CH4, okay? So with CH4, that's how many electrons you have. Okay? That's the Lewis diagram. So you've got 8 valence electrons, and those 8 valence electrons can move around and cause this part to become a little bit more positive, this part to become a little bit negative, as these electrons are vibrating, because remember, these electrons are not standing still. Then if you have CF4, you can go check this out for yourself, but the Lewis diagram of CF4 is like this. You've got these electrons on the outside. Now, because you've got more electrons, there's more chances for these random movements to take place, and so you've got more of these positives and negatives happening more. There's more chance of them happening. And so if you have two CF4 molecules next to each other, there is going to be stronger attraction between these two molecules, because at any given moment there is a higher chance that this molecule and this molecule has like a lot of positives and negatives taking place, because there are more electrons moving around randomly, creating those positives and negatives. Whereas if you had this molecule and another one, there is less chance of creating positives and negatives in this one over here. Okay, so I hope that makes sense. Heavier molecules means that there's more electrons, and with more electrons you've got more of that random movement taking place, and then you've got therefore more chances of London forces, and so the overall London forces become stronger, because maybe in this molecule here you've got a slight positive and a slight negative happening over here. So there's an attraction, okay? But in this molecule, or in these two, this one and this one, you might have a positive or negative here, a positive there, a negative there, a positive there, a positive there, a negative there, blah, 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 blah. And so you've got much more attraction taking place at any given moment. So heavier molecules, more electrons, more chances of these random asymmetries to take place, and so there's going to be stronger London forces. Okay, so if we now go and look at the masses, so if you look at CH4, it's going to be a carbon which has a mass of, where's carbon here, 12, and then there's 4 hydrogens. That one would have a mass of 16. CF4 would have a mass of 1938.76 plus 12, so it's at 88. And then CCl4, that's a heavy one, okay, so 35.5 multiplied by 4 plus 12 is 154. Okay, so we can see that the heaviest one, remember, heavy, more electrons, more chances for those temporary dipoles to take place. You can see it's got the largest boiling point. Now, some of you are like, yo, but bro, this one's 182, this one's 23. Guys, there's negatives. So that's negative 182. So that's much colder than this one, okay? So this one has a much larger melting point, sorry. Because remember that when you have CCl4, okay, so let's put CCl4, and then let's put another CCl4, okay? Now remember, there's a whole bunch of electrons. So we said that because of all those electrons, there's going to be lots of positives and negatives, and so there's going to be a lot of London forces taking place over here. So if you have all of these London forces, it's going to be quite difficult to separate these two molecules from each other. And remember, when you melt, you are going from a solid where everything's close together to a liquid where everything's a little bit further apart. So to be able to melt something, you have to be able to overcome all of these forces. You've got to be able to separate these molecules from each other. So if the molecules are really heavy and there's lots of electrons, that means that there's lots of these temporary dipoles happening, and so the London forces are quite strong, and so you need more energy to be able to separate them. Now, what do we use for energy? We use temperature. The more hot you can make it, the more energy you have. So that is what they're saying here, is that if you would like to separate CCl4s from each other, you have to make it hotter than when you want to separate CH4s. Because with CH4s, some of you are like, oh, Kevin, you're going to go draw this all again. Come on, bro. Sorry, guys. I just really want to explain this nicely. Come on, Kevin. So with CH4s, there aren't as many temporary dipoles, so you don't need as much energy to separate them, and that's why the melting point is not as high as you have it for CCl4. Okay, so we can say something like all molecules in the table are nonpolar. Okay, so they will all contain London intermolecular forces. London forces increase in strength with an increase in molecular mass. Okay, we now need to just say that we can say that CCl4 mass is larger than CF4, which is larger than CH4. Okay, so we can say something like, therefore, the melting point of CCl4 is larger than CF4, which is larger than CH4, as more energy is needed to overcome the stronger intermolecular forces. This one says, which molecule in the table will have the highest vapor pressure? Okay, so let's talk about vapor pressure for a little bit. I want you to think about vapor pressure. Think about vapor. Is it liquid, solid, gas? Well, that's more of like a gas. So if you have a room, okay, that is filled with a lot of gas, then we would say that it has a very high vapor pressure. If you have a room that has a very little bit of gas, and most of it is in the liquid phase, and there's only a little bit of gas, then we would say low vapor pressure. Vapor pressure is for gases. So if there's a lot of gas, so lots of gas, then we say high vapor pressure. Okay, so if there's lots of gas, high vapor pressure. If there's a little bit of gas, then there's a low vapor pressure. So you need to think about which of these molecules are going to be easier to turn into a gas. Well, remember, to turn something into a gas, you have to first take it from a solid where the molecules are very close together. Then you have to separate them a little bit so that they become a liquid. And then you need to be able to separate them even further so that they become a gas. So we said that CH4, did we say that the London forces are stronger or weaker compared to CCl4? Well, if you remember correctly, we said that these ones over here have the weakest London forces. Then it's these ones, which are a little bit stronger, and then these ones are the strongest. Remember, because of the size and the mass and the electrons. So which ones are going to be easier to pull away from each other? Because remember, if you have two CH4s next to each other, okay, we said that because there are not that many electrons, the temporary London forces are not going to be that many. So you might have you won't have too many. So to be able to separate this is not going to be very difficult. Okay? Whereas, now don't worry, I'm not going to go draw the whole thing, but if you have like CF4 or CCl4 actually, and you had all those, okay, I'm just going to quickly do it. If you had all those electrons, right? These ones are going to be very difficult to separate because there are so many temporary London forces happening. So, these ones are easy to separate. These ones are very difficult to separate. So, if you had to walk into a room filled with CH4, you would probably find more gas. Because remember, to make a gas, you have to separate the molecules from the solid to the liquid to the gas. So, because these ones are easier to separate, you would find more of these in the gas phase. Whereas these ones over here are difficult to separate, so most of them are going to be in the solid or in the liquid phase at a certain temperature, if that makes sense. So you would expect the vapor pressure of this one to be more because there will be more gas at a specific temperature of this one. Okay? So it says here, which molecule on the table will have the highest vapor pressure? We will definitely say CH4. And that is just because it has the lowest melting point. Okay? Because they said explain by referring to the data in the table. So we can just say it has the lowest melting point. Okay, water is a smaller molecule than CCl4. What that means is they're trying to say that it is lighter. So it has less electrons. Water is only 18 grams per mole. Whereas this one we said was like a huge amount. Remember, it was like 154 grams. But water has a higher melting point than CCl4. Explain this observation by referring to the type of intermolecular forces. Now, I'm so happy they're including this question because we said this one has a mass of 16. We said this one has a mass of, I think we said 88. And then you've got water, which has a melting point. What is the melting point of water? Do we know? Yep, it's 0. When you go from ice to water, it's 0. Water is only 18 grams. Now, Kevin, I'm confused, brother. You told us that as the mass increases, the melting point increases. So if you had 18 grams over here, then surely water should be somewhere in between 182 and 150, negative. But that argument that I was showing you guys, where I was showing you all of those electrons and everything, I was talking about London forces. That is a property of London forces. London forces become stronger the heavier the molecule because of all of those electrons. But water is not only London forces. We need to remember that water is a polar molecule. So it has got London forces. All molecules have London forces. I wonder if you knew that. Because there's always going to be electrons that are moving around. But water also has, because it's a polar molecule, it also has stronger intermolecular forces. In fact, water has hydrogen bonding, which is extremely strong compared to London forces. So even though CCl4 is a much larger molecule and it's got much stronger London forces than water, water is still going to be stronger due to the hydrogen bonding. Because hydrogen bonding is much stronger than London forces. So it says, explain this observation by referring to the type of intermolecular forces. So we can just say that water has hydrogen bonding. And you could also say it's got London forces. Every molecule has London forces because London forces simply arise due to the movement of electrons. And all molecules have electrons. So water has hydrogen bonding and London forces, whereas CCl4 only has London forces. This one says, write down the name of the intermolecular force that will exist if you had a mixture of H2O and CCl4. Okay, so let's put a H2O molecule over there, and then let's put a CCl4 molecule. Okay, so we know that this is a nonpolar. And we know that this is a polar. So what do you get when you put a polar next to a nonpolar? Well, you get a dipole, because this is a polar molecule, and we call that a dipole. And then we call it a induced dipole. Okay, we have studied that before, right? When you put a polar next to a nonpolar, you get a dipole-induced dipole. But what does that actually mean? Let me explain. What it means is that we definitely know this is polar. So it's got all these positives and these more negative parts, like that. Okay? Now, with this molecule, it is overall non-polar. So there's no more positive part and more negative part. Overall, it is just completely neutral. So what happens is that when this water molecule comes floating along, okay, let's say for example the water molecule comes floating along like this, and it's got its negatives and its positives. then what would happen is that these electrons around here, or actually all of the electrons, as soon as this water molecule starts approaching with these positive parts facing like that, you would find that a lot of the electrons would start going towards that area because of just the opposites attract. So what happens is that this area of the this area here of the CCl4 is going to end up becoming very negative. Why? Because all the electrons are gathering over here, and it's going to leave the other areas in a more positive kind of way because they're losing electrons. So what that means is that while this water molecule is in the area, it will cause this molecule to actually become a polar molecule. Okay? Because it's got a more negative side and a more positive side now. So we say that you have a dipole molecule inducing a dipole in another molecule. So it's called a dipole-induced dipole. And then as soon as this water moves away again, then all of this will just go back to normal. Okay? So this is just a temporary dipole.